Let's look at OpenStack's College Physics, Chapter 16, Problem 38. A novelty clock has a 0.01 kilogram mass object bouncing on a spring that has a force constant of 1.25 newtons per meter. What is the maximum velocity of the object if the object bounces 3 centimeters above and below its equilibrium position? B. How many joules of kinetic energy does the object have at its maximum velocity? So let's write down our knowns and unknowns. And so what we know is that the mass that hangs from a spring under a clock is 0.0100 kilograms. And the spring has a spring constant K of 1.25 newtons per meter. Then we know that the object bounces 3 centimeters above and below its equilibrium position. So that would make that value the amplitude of motion. So A is 3.00 centimeters. And in part A, we're looking for the maximum velocity. So we want V max. And in part B, we're looking for the kinetic energy at V max. All right, so I drew a diagram here. So here's the clock. I'm assuming this is what it's supposed to be like, kind of like a grandfather clock, but instead of a simple pendulum, it has a mass hanging from it. So it has a spring with a mass hanging from it. So this mass at the end will oscillate back and forth and will produce this simple harmonic motion. So I have my cheat sheet on the right here. I know mass and spring constant, so from this we can find the omega, the angular frequency of the motion, and we're looking for velocity, so here is the equation for velocity. So I'm going to write that down. I have V is negative omega A sine omega t. And since I'm looking for V max will be when the trig function in here will be at its maximum point. Well, the maximum point is plus or minus 1. So that means that V max is plus or minus omega A. And I will just leave it as a positive value because I'm not really interested in the direction in which the object is oscillating. That's what the plus or minus stand for. So I know that omega is square root K over M, and then I multiply that by A, and I can solve for the V max. So that is square root of 1.25 newtons per meter divided by mass, which is 0.0100 kilograms, and the amplitude is 3 times 10 to the negative 2 meters. So multiplying all of this together gives us a V max of 0.335 meters per second. So that was for part A. Now in part B, we're looking for the kinetic energy at the maximum velocity. So kinetic energy is given by 1/2 mv squared. So then we have 1/2 mass is 0.0100 kilograms. V is 0.335 meters per second, quantity squared. And we end up with 5.61 times 10 to the negative 4th joules. So that is the kinetic energy. Now, I want us to look a little bit at kinetic energy and potential energy in a spring. So if I start out with an unstretched spring, and then I stretch it, and I have a mass at the end of it, then this is the maximum stretch from equilibrium, and when it is fully stretched like this, I'm holding it still in place. So the velocity here is 0, but the spring is stretched to the maximum, which means that the restoring force is going to be maximum. So that means that the acceleration is maximum. then as the spring passes through equilibrium, that is where the velocity becomes max. And since there is no restoring force acting at this point, the acceleration is 0. So there is going to be a conversion of energy from potential to kinetic to potential to kinetic in this motion. So the extremes, extreme is not here, it's somewhere here. So the extremes have potential energy and the equilibrium position has kinetic energy, because at the extremes, velocity is 0 for a split second and the acceleration is maximum. And while it's going through the equilibrium over here, then the velocity is maximum and the acceleration is 0.